Hi Year 11 and welcome to our fourth lesson for the topic of functions. In this lesson we're going to look at quadratic functions. We've got quite a lot to get through. We're going to start by looking at the quadratic polynomial, the features of a parabola, the roots or zeros of a quadratic function, and the forms of a quadratic function. Then we'll look briefly at transformations, how to form a quadratic, the discriminant, and finish off with intersecting functions. Let's start with some definitions. The algebraic expression y equals ax squared plus bx plus c, where a is not equal to 0, is called a quadratic polynomial. And the graph of y equals ax squared plus bx plus c is called a parabola. And we see this parabolic shape many times in real life. It is the way objects fall under gravity, and we also use it in construction. Now the parabola has the following features. It has exactly one y-intercept. That's where it cuts the y-axis. It can have 0, 1, or 2 x-intercepts. It has what's called concavity, and we'll talk about that in a little bit. It has an axis of symmetry, so a line over which it is symmetrical. And it has a vertex or turning point. To find the y-intercept, we substitute x equals 0 into the equation. So into ax squared plus bx plus c, we substitute x equals 0, and that's going to give us y is equal to c. So the y-intercept is the point 0, c. If we want to find the x-intercepts, we substitute y equals 0 into the equation. And that's the same as solving ax squared plus bx plus c equals 0. We can do that either by factorising or using the quadratic formula. Let's have a go at graphing y equals x squared plus x take away 6. We'll start with the y-intercept. So we substitute in x is 0, 0, 0, y is equal to negative 6. The y-intercept is 0, negative 6. Now let's do the x-intercepts. We substitute y is equal to 0. 0 equals x squared plus x take away 6. Now, to solve this quadratic, we need to factorise this. Into brackets, we get x minus 2 multiplied by x plus 3 equals 0. Now, we're going to use our null factor law. Either this is equal to 0 or this is equal to 0. What makes 0 here? 2. What makes 0 here? Negative 3. And so the x-intercepts are the points 2, 0 and negative 3, 0. And if we plot those points, negative 3, 0, 2, 0, and 0, negative 6, we can draw our parabola. Now, we talked earlier about concavity. The graph of y equals ax squared plus bx plus c can either be concave up, so that's where the tails point upwards, and that's if the coefficient of x squared is positive. Or it can be concave down, the tails point down, and that's when the leading coefficient, or the coefficient of x squared, is negative. So let's graph y equals negative x squared plus 6x. Let's do the y-intercept first. X is 0, 0, y is equal to 0. So the y-intercept is the point 0, 0. Now the x-intercepts, we're going to substitute in y is equal to 0. Factorise and solve. X is either equal to 0 or 6. So the x-intercepts are 0, 0 and 6, 0. You can see how we've got the same point here. Now we actually don't have enough information to be able to graph this. We've got 2 points, but we can't tell whether the graph is going to be concave up or concave down. So we need to look here and get some more information. The coefficient of x squared is negative, so this graph is going to be concave down. Now you might be looking at this graph and thinking, well, how do you know that it's going to go through this point, 3, 9? And we're going to look at that next. So the axis of symmetry occurs through the vertex, and the vertex is the maximum or minimum point of the parabola. The axis of symmetry is equidistant from the two x-intercepts, if there are two. And it has a formula. So the formula is x is equal to negative b on 2a. Now that's not given for you on your reference sheet. However, the quadratic formula is given. And just here, inside the quadratic formula, you can see the axis of symmetry formula, minus b on 2a. Now if you want to find the coordinates of the vertex, all we do is use the axis of symmetry formula, and that's going to give us the x coordinate. Then we substitute back into the equation and we will find the maximum or minimum value, or the y coordinate. So returning to this question where we asked, well, how do we know how high up to make this point? We're going to use the axis of symmetry formula to find the x coordinate, then substitute back into the equation to find the y coordinate. So our axis of symmetry formula is negative b on 2a. So negative 6 on 2 lots of negative 1. And so x is equal to 3. So there's our axis of symmetry. And we can see this quite clearly from the graph, but suppose we weren't given the graph, then we would use the formula. Now substituting x is equal to 3 back into here, our y coordinate is 9. So the maximum point is 3, 9. Now the roots or zeros of a quadratic equation are the x-intercepts of the graph, and they occur when y is equal to 0, hence why they are called zeros. This word, roots, that's actually related to the square root or the nth root. But we can find the roots or zeros either by factorizing or using the quadratic formula. Here's an example. Use the quadratic formula to find the zeros of y is equal to x squared plus 5x minus 7, giving your answers to one decimal place. So in this case, a is 1, b is 5, c is negative 7. Let's substitute in. We end up with minus 5 plus or minus the square root of 5 squared, take 4 times 1 times negative 7 all over 2 times 1. Tidying that up, we end up with negative 5 plus or minus the square root of 53 all over 2. And putting this into the calculator firstly with the plus sign and then secondly with the minus sign, we get 1.1 and negative 6.1. Now there are two standard forms that we use to express quadratic functions, and they have different advantages and disadvantages. So firstly, there's general form. We've been using that quite a bit, and it is useful if we want to find the y-intercept, which is going to be the constant term. So the y-intercept is 0c. Both of them are useful if we want to look at concavity because we have a coefficient of the x squared term. And vertex form is really useful if you want to know the vertex because it is what makes 0 here, h, and the constant term at the end, k. So let's have a go at converting general form to vertex form. We want to write y is equal to x squared plus 6x plus 10 in vertex form and state the coordinates of the vertex. So we are going to complete the square. You can see how I've moved the 10 over and left space to complete the square. I look for the term in x and find the coefficient, which is 6. Halve it, square it. Half of 6 is 3, squared is 9. Now you can borrow a 9 from the 10, or we can go plus 9 minus 9. Whichever way, it doesn't matter. Complete the square, we get x plus 3 all squared plus 1. And so our vertex is what makes 0 here, negative 3, and the constant term at the end, plus 1. Now vertex form is very useful for graphing parabolas where there are no x-intercepts, and that's the case here. We can easily find the y-intercept. X is 0, y is equal to 10. But if we substitute in y is equal to 0, we can't find any solutions to that equation. So there are no x-intercepts. So if we went to graph this, we've only got one point. We do know concavity though. We know that it's concave up, but it's still not enough information. So converted into vertex form, we have another point now. We have negative 3, 1. So having a look at the graph, here is our y-intercept, 0, 10. Here is our turning point, negative 3, 1. And it's symmetrical about that line, x is equal to negative 3. Okay, let's move on to transformations. There are two transformations that we can make with parabolas, and they're easily seen if we write our quadratic in vertex form. So there is a horizontal or vertical translation, so that's a shift across or up and down, and there's a dilation, which includes reflection. So let's look firstly at vertical translations. All we do is take our normal graph y equals x squared and add a number on the end. Now, if this number on the end is positive, then the graph will move up, like this one, y equals x squared plus 1. If the number on the end is negative, then the graph moves down, like this one, y equals x squared take away 2. We can also translate a graph horizontally, and instead of y equals x squared, we will have y equals x minus a all squared. So this graph will translate horizontally by a units. Now, if a is positive, then the graph moves to the right. And if a is negative, then the graph moves to the left. I always like to think that it moves to what makes 0. What makes 0 here? Negative 2. So you can see how it's moved from 0 to negative 2. And we can stretch, compress, or reflect a parabola. And these are called dilations. Given y equals x squared, if we change the coefficient of x squared, this will stretch or compress the graph. If p is greater than 1, then the parabola gets skinnier or steeper. You can see that with this blue graph here. If p is in between 0 and 1, this makes the parabola flatter or fatter or wider. And we can also reflect the graph over the x-axis by making the coefficient of x squared negative. You can see it turns from concave up to concave down. And we say y equals negative x squared. Is the graph of y equals x squared reflected in the x-axis? So here's an example. Describe the transformations with y is equal to 4 take away x minus 2 all squared and sketch the graph. All right, I'm going to turn this around just a little bit into vertex form. So y is equal to negative x minus 2 all squared plus 4. And we can see a few things. We have got a reflection in the x-axis. It's concave down. Here we can see a vertical translation of plus 4, so it's going up. Here we have a horizontal translation of plus 2, so it is going to the right. So if we draw our normal y equals x squared, then this thing is sliding 2 units this way, 4 units up this way, and flipping upside down. So we want to sketch it. Let's just put some coordinates in. It's going to have its turning point there. It's going to go like this, and probably ought to find the y-intercept. Let's substitute in x is equal to 0. We end up with y is equal to negative 2 all squared plus 4, which is 0. So this is the graph here. Now we can find the equation of a parabola if we're given enough information. And recall, with a straight line, all we need is 2 points to fix a line. There is a unique line that goes through 2 given points. With a parabola, all we need is 3 points. There will be a unique parabola that goes through these 3 points. However, we could be given different types of information. So 3 points, for example, or the axis of symmetry, 1 point, and the concavity, or the vertex, the concavity, and either the x or y intercept, or just the intercepts. Here's example 1. Find the equation of the parabola that passes through the points 0, 9, negative 2, 17, and 3, 12. Now we're just going to use our general form, y equals ax squared plus bx plus c. I can see here that I have the y-intercept, and so c will equal 9. So I'm going to substitute that in. Now when I substitute both of these points in, I'm going to end up with simultaneous equations with 2 unknowns. So let's substitute in negative 2, 17. 17 is equal to a times negative 2 all squared plus b times negative 2 plus 9. Tidying that up, I get 4a take away 2b is equal to 8, and I can divide everything by 2. So there's my first equation. Now let's substitute in 3, 12. 12 is equal to a multiplied by 3 squared plus 3b plus 9. Tidying it up, and I can divide everything by 3. And that gives me my second equation. Now I'm just going to use process of elimination. So because I have different signs for the b term there, I'm just going to add these two together. So I get 2a plus 3a is 5a, 4 plus 1 is 5, and so a is equal to 1. Now let's substitute back into equation 2. and I'll get 3 plus b is equal to 1, so b is equal to negative 2. And so my quadratic equation is y is equal to x squared take away 2x plus 9. Here's example 2. Find the equation of the parabola that has axis of symmetry x equals 1, passes through 0, negative 1, and negative 2, 15. Now in this case I'm going to use vertex form because I have the axis of symmetry. So that's the x-coordinate of the vertex. That's actually h. h is 1. And now just like before, I'm going to substitute both of these points in and form simultaneous equations in two unknowns. So substituting in 0, negative 1, I end up with negative 1 equals a, 0 take away 1 is negative 1 all squared plus k. Tidying it up, I get a plus k is equal to negative 1. There's my first equation. Now let's substitute in negative 2, 15. End up with 15 is equal to a multiplied by negative 2 take away 1 is negative 3 all squared plus k. Tidying it up and turning it around, I end up with 9a plus k equals 15 as my second equation. So this time I have got the same sign, so I'm going to subtract. And furthermore, I'm going to go from the bottom upwards to avoid negatives. 9a take away a is 8a, k's are gone. 15 take away negative 1 is 16. Divide both sides by 8, a is equal to 2. Substitute back into equation 1. 2 plus k equals negative 1, k is equal to negative 3. Therefore, the equation is y is equal to 2 outside of x minus 1 all squared, take away 3. Let's move on to the discriminant. Solve the following using the quadratic formula. So I'm going to go through this quite quickly. When I have substituted in a, b, and c and tidied it up, I end up with negative 6 plus or minus the square root of 16 all over 2. And then working each of those out, I end up with negative 1 or negative 5. And we say in this case that the roots are different, they are real, and they are rational. In this case, I end up with x is equal to negative 6 plus or minus the square root of 32 all over 2. And putting this into my calculator, I end up with negative 0.17 and negative 5.83. And we say in this case the roots are different. They are real numbers, but they are irrational. And with this one we get x is equal to negative 6 plus or minus the square root of negative 4 all over 2. And we can't have a negative under the square root, so we say that the roots are not real. They don't exist. And then finally, x is equal to negative 6 plus or minus the square root of 0 all over 2. And this 0 wipes out the plus or minus because we can't have plus or minus 0, and we end up with only one answer. But we say the roots are real, they are equal, like they're negative 3 and negative 3, and they are rational. Now there is a shortcut. We can predict the nature of the roots of the equation by working out the discriminant. And that's the part that's under the square root in the quadratic formula. So instead of doing the whole thing like we just did, we just have to work out b squared minus 4ac. So this is called the discriminant and has the symbol delta, which is a Greek letter. Let's go back to these questions and have a look at the discriminant. So here it is 16. Because it's greater than 0, we have different roots. They are real, and because 16 is a perfect square, they are rational. Here the discriminant is 32. It is greater than 0, so they are different and they are real, but 32 is not a perfect square, so they are irrational. Here the discriminant is negative 4, so the roots are not real. And here the discriminant is 0, so that's going to wipe out that plus or minus and give us only one answer. So when we've got 0 here, we have real and equal roots. So I've summarized all that information in this diagram. Here's the discriminant. If it is less than 0, the roots are not real. Equal to 0, the roots are real and equal. Greater than 0, the roots are real and different. Furthermore, if we have real and different roots and the discriminant is a perfect square, then the roots are rational. If it is not a perfect square, then the roots are irrational. So we might get a question like this. Describe the nature of the roots of y equals x squared take away 4x take away 2. So we start by working out the discriminant. It is negative 4 all squared, take away 4 times 1 times negative 2, which is 24. Right, greater than 0 tells us they will be real and different. 24 is not a perfect square, so they will be irrational. In this case, the discriminant is 5 squared, take away 4 times 2 times 3, which is 1. Again, greater than 0, so real and different, but 1 is a perfect square, so they'll be rational. And this one, the discriminant is negative 2 all squared. Take away 4 times 3 times 1 is negative 8. They are not real. The discriminant is also useful in determining the sign of the quadratic function. If the discriminant is negative, then there are no real roots, there are no x-intercepts. The parabola doesn't cut or even touch the x-axis. Furthermore, if the leading coefficient a, so that's the coefficient of x squared, is greater than 0, the quadratic is called positive definite, because the leading coefficient being greater than 0 means it's concave up. The discriminant being negative means it never touches the x-axis. So for every y value, this quadratic function is positive. If, however, the leading coefficient is less than 0, we say the quadratic is negative definite. It's concave down. It never touches the x-axis. Every y value will be negative. Now, if the discriminant's not negative, then it does touch or cut through the x-axis. So we say the quadratic is indefinite. It's got bits that are positive and bits that are negative. And even here, where it just touches, the y value here is 0. So it's not positive or negative. So even this one is indefinite. Here's an example. Show that 2x squared take away 3x plus 9 is greater than 0. Now you could do this question by completing the square, but it would be a bit ugly with fractions. An easier way is to work out the discriminant and then talk about the concavity. So the discriminant's easy. That's just negative 3 all squared take away 4 times 2 times 9, which is negative 63. Less than 0 never cuts the x-axis. So it's either going to be definitely positive or definitely negative. We just got to look at the concavity of it. So since a is equal to 2 is greater than 0, it's concave up, it is positive definite. Therefore, 2x squared take away 3x plus 9 is always greater than 0. Okay, last bit. Find the point or points of intersection between the parabola y equals x minus 1 in brackets multiplied by x minus 3 in brackets and the line y equals 7 minus x. So if we want points of intersection, we are talking simultaneous equations. So I'm going to put this equal to this, and then I'm going to solve it. Let's expand the left-hand side, and taking the 7 minus x over the other side, I end up with x squared take 3x take 4 equals 0. Factorize, and we have null factor law. Either this is equal to 0 or this is equal to 0. So x is 4 or negative 1. Now we want to find the points of intersection, so we need the y coordinates as well. So substitute these back into this line. So at x equals 4, y is equal to 7, take away 4, which is 3. At x equals negative 1, y is equal to 7, take away negative 1, which is 8. And so the points of intersection are 4, 3, and negative 1, 8. And here's our last example. Consider the quadratic function y equals x squared plus 3x take away 1. The line y equals x plus k either cuts it once, twice, or never. For what values of k will there be 2 points of intersection? All right, we're going to do exactly the same thing we just did and put this equal to this. And taking this over the other side, we end up with x squared plus 2x take away 1, take away k equals 0. We want to know when this quadratic has 2 solutions. We just did something very similar to that. Of course, we want to work out the discriminant. So be careful with c here, it has 2 terms, so make sure you put that in brackets. The discriminant is b squared take away 4 times a times c. Now expanding that out, we end up with 4 plus 4 plus 4k, which is 8 plus 4k. We want 2 values, 2 distinct or 2 different roots, so we want this greater than 0. And it's pretty easy inequality to solve. 4k is greater than -8. And here's our last example.
Than -2.
Consider the quadratic function y equals x squared plus 3x take away 1. The line y equals x plus k either cuts it once, twice, or never. For what values of k will there be 2 points of intersection? All right, we're going to do exactly the same thing we just did and put this equal to this. And taking this over the other side, we end up with x squared plus 2x take away 1. Take away k equals 0. We want to know when this quadratic has 2 solutions. We just did something very similar to that. So I actually put this into Desmos so that you can have a look at it. We have our parabola, y equals x squared plus 3x take away 1, and our line, y equals x plus k, and I've made k into a slider. Now have a look what happens when I make k go down towards -2. It just touches at one point. That's called a tangent, so there's only one solution. But any k value greater than -2, that line cuts the parabola in 2 places. Okay, that's it for this lesson. Our next lesson is on nonlinear relationships.